Hey, this is Brock Lemires, and in this video I want to do a circuit analysis example of a circuit with a diode in it using the constant voltage drop model that we've discussed. Okay, so here's the challenge before us. This is the circuit, and this at first glance appears to be very complex because it's got a lot of different unknowns in it. And what we want to do is I want to analyze this circuit with the following given. Okay, so the power supply is a DC voltage source that's 3 volts, and I know the values of the resistors. Okay, so a R1 is 100, R2 is 50, and R3 is 100. And I know the forward voltage of the diode. And so what I'm trying to do is figure out what is the current through the diode, and I want to know what voltage, what V1 is, V2, and V3. And once I know all this, I can solve for I1 and I2, but just for now, let's just go for the voltages and the current through ID, okay? And we want to use the constant voltage drop model to solve this. Okay, so here we go. I'm going to walk through every single step. Hopefully it'll be clear. All right, so now, first and foremost, when we use the constant voltage drop model, we have to ask the first question, is it on? So I have to figure out if the voltage that the power supply is providing is sufficient to turn on the diode. And what does it mean for the diode to be on? It means that the voltage that has been created across it is 0.7. But when the moment that it turns on, there actually won't be any current through it. And so here's what I mean by that. If I come along, I'm going to have some power supply, and I don't know what it is yet. Okay, I'm figuring out what the minimum power supply is in order to turn that thing on. Okay, and so I'm going to have a circuit like this, and I've got this diode on. Okay, I've got this diode right here, and it is going to have 0.7 across it. So you basically start with 0 volts right here for the source, and you crank it up, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and it gets high enough that you are able to put 0.7 volts across the diode, which is its forward voltage, and then once you increase beyond that, current will start flowing. But the moment that this diode goes from being off, where the voltage across it is less than 0.7, to being on, where the voltage across it equals 0.7, is when the current right here is equal to 0. Okay, so that is the way that we model the instantaneous point in time at which this turns on. So when I look at this, what I do is I take this information of that this has 0.7 across it and it has no current through it, and I basically reverse calculate what would be the bare minimum, the minimum DC voltage at the power supply to make this turn on, and then I can go back to my circuit and say, okay, am I above that minimum voltage? And if so, it's on, and if I'm below it, it's off. So here we go. Let's go ahead and do this. So I've got a 100 ohmer and a 100 ohmer and a 50 ohmer, and I look at this information right now and I say, what am I going to do? Okay, first and foremost, all right, if the current through the diode is 0 at this instant that it turns on, that means there's no current through this resistor right here, R3. And that means I can say V3 is equal to 0 times 100. V is equal to IR, and that is equal to 0 volts. So I know immediately this is 0 volts across that resistor. And that's cool, okay? So that is huge right there because I know right away that that's it. Now what I'm going to do is the following. I am going to do KVL around this loop right here because I know the voltage across the diode. Okay, I know this is what I want across the diode, and I know there's no voltage right here, so I can come along and I can actually say, I can find out immediately what V2 is. So if I do KVL around this loop, what I get is I go across V2 from minus to plus, so it's a rise, and then I'm going to drop across 0 volts, and then I drop across 0.7, and immediately I have V2 is equal to 0.7 volts. And it's like, okay, so I've solved for V2. It's like, okay, that's cool. That's getting me closer to figuring out what the minimum voltage is. So now let's think about what's happening right here. At KCL, I'm going to have a current right here, okay, that comes from the supply, some current, and it is going to come to this junction, and I know that there's no current going this way. That means that this current is going to go this way. So there's really only one current that's flowing in this circuit at the very instant that this diode turns on, and we'll call it I. We'll just call it I. Okay, so let's solve for I using Ohm's law at V2. So I'm going to do Ohm's law right here. And I can say from Ohm's law that V2 is equal to I times R2, which I'm just going to plug in as 50. And now I look at this and I'm like, well, I already know V2, so I can say 0.7 is equal to I times 50, and I can say I is equal to 0.7 over 50. Then I bring out a buddy and I say 0.7 divided by 50. And I end up with 14 milliamps. Okay, and now why was that important? It's important because I'm ultimately trying to find V minimum. I can now use that to figure out what V1 is. So if I come over here and I got V1, that current 14 milliamps is also going through V1. So I can come along and I can say, all right, V1 is equal to I times R1, which is 100. And I just simply plug that in. So I got 14 milli multiplied by 100. And I get V1 is equal to this times 100, and I'm left with 1.4 volts. So why did I care about V1 and why did I care about V2? Because if I do KVL around this loop right here, I can say KVL around this loop is going to be this. I'm going to have minus to plus V minimum as a rise, and that's going to be equal to a drop across V1 plus a drop across V2, and I have just now solved for V1 and V2. So I can come in here and I can say, okay, I got 1.4 volts right there plus 0.7, and I add those together and I get 2.1 volts. So V minimum is 2.1 volts. What does that tell me? That tells me that the power supply has to be at least 2.1 volts in order to induce a voltage across the diode that is 0.7 and get it to turn on. If I am above 2.1, it's on, life is good. If I'm below it, no good. Okay, no life is good. So it's not on. So now we have our information that we wanted, which is it on? And the answer is yes. Why was that so important? Because then that now says that I can use the constant voltage drop model to solve this circuit. And what does the constant voltage drop model mean? Well, actually, I might not have said this. How come it's on? It's because the power supply in our circuit is 3 volts. So 3 volts is higher than 2.1, and that is it. So that it is on. So in this circuit, I know I can draw this and I can say plus or minus 3 volts means that diode buddy is on. Okay? All right, so now let's go back to our circuit. All right, so I got myself plus or minus V1. I got 100 ohmer there. I got, redraw this right here, and I got myself plus or minus V2, and I got myself 50 ohmer. And now I get over here, and I'm like 100. I got plus or minus V3. And now check this out. I am now going to replace the diode with the constant voltage model drop for a diode that is on. And remember, what that means is I replace it with a power supply, a DC power supply that has a voltage equal to the forward voltage. So that diode now looks like a 0.7 volt DC voltage that isn't going to change regardless of how much current flows through it. It also means that current can flow through it and it has 0 resistance because that's the property of the DC voltage source. So now all I have to do is say, okay, I have this circuit and I'm ready to start solving it. So now I'm just going to start writing KVL and KCL in order to solve it. Now here's the whole thing. This is something where you develop not even, I guess you could say intuition, but this looks daunting because there's so many unknowns and so many variables. But so you have to write a bunch of equations to solve for the unknowns. But let's start. First of all, what are the unknowns? Well, I'm going to have I1, I'm going to have I2 and ID, and I have V1, V2, and V3. So I have 6 unknowns, okay? So I need 6 equations, okay? Now, at this point, you may stop the video and cry, right? No, just bear with me. We can do this. So let's do the following, okay? So I'm going to come around here and I'm going to try to be a little bit organized. And so here's what I'm going to do. I'm going to write, where did the equation come from? Well, I've got KVL and KCL, and I also have Ohm's law. So the thing about 6 equations and 6 unknowns is that you always get Ohm's law ones for free. So Ohm's law is really easy. You're going to get V1 is equal to I1 R1. That's an equation. V2 is equal to I2 times R2. That's an equation. V3 is equal to ID times 100. That is an equation. So you get 3 of these right away. But let's do this. Let's write the first equation as the following. Let's do KVL, around loop 1. So this is going to be kind of loop 1. So this is equation 1. All right. Now, here we go. I'm going to write this, and I'm going to come around the loop and sum my rises and sum my drops and set them equal to each other. So I'm going to come up through 3 volts, so minus plus, that's a rise. So I've got a 3 over here, and then I'm going to drop from plus to minus across V1, plus to minus to V2. So I have V1, 3 is equal to V1 plus V2. So that's my first equation, okay? That is KVL on loop 1. All right, let's do our second equation. This is going to be loop 2, and I'm going to label this thing equation 2, and I'm going to come along and I'm going to do the KVL. So here I go. I'm going to go round clockwise. I go from negative to positive through V2, so that's a rise. And then I'm going to drop across V3 because I go plus to minus, and I drop across the diode voltage, which is 0.7. So it looks like this. V3 plus 0.7. And that is it. That is perfectly legal. That is the constant voltage drop model, because we're modeling this thing, this diode, as a 0.7 DC voltage source, because that's what it looks like. It develops 0.7 and then it clamps. All right, let's do the last one, which is going to be equation 3. And this one now is going to be KCL. KCL, and it's going to be right here. So I'm going to do KCL at this node, and that'll relate the currents to each other. Okay, so I got I1 coming in, and then I've got I2 going out, and ID going out. All right, so there's my 3 equations, and I also have 3 more equations, if you wouldn't mind. Let me just write them up here. They're going to be pretty easy because they're just Ohm's law, right? So I'm going to get V1 is equal to I1 times R1. And let's just plug in the values for that right now. So V1 is equal to 100 times I1. But I'm going to put the 100 in front just because then it looks more like the way we draw our math. And then let's do V2 is equal to I2 times R2, but again, let's just rewrite it where we plug in R2, which is 50. So I'm going to have 50 times I2. And then finally, we got V3 is equal to ID times R3. And again, let's rewrite it. So we got, we're plugging 100 into R3, so we'll get 100 times ID. I now have 6 equations and 6 unknowns. And so now what we got to do is we got to start plugging them into each other and solving for variables. So let's start by looking for ID. Okay, so once we know ID, we know a whole lot of stuff. So now let's see how we can plug things into each other. If I decide to go for ID, then what I need to do is I need to start getting things in terms of currents. So watch what I'm going to do right now. I'm going to plug these equations, we'll call them 4, 5, and 6, into these 2 equations, and then that will remove the voltages. So let's go ahead and plug these in. And so follow along. Here we go. So I'm going to come down here and I'm going to plug in these Ohm's law equations into here. So I'm going to get rid of V1 and V2. So I'm going to now have 3 is equal to, and I plug in V1, it's 100 times I1. Plus, now I substitute in for V2, and that's going to be 50 times I2. Okay, all right, life is good. And now let's come over here and let's do this one. So now I'm going to have V2 is going to be 50 times I2 is equal to V3, which was ID, God dang it, 100 ID plus 0.7. Okay? All right, how's that feel? Actually, that felt pretty good, because now look at what I'm left with. I now have 3 equations, and they're in terms of I1, I2, this one's I2, ID, I1, I2, ID. I now immediately have 3 equations and 3 unknowns. So just by substituting those into these, I've already reduced the number of unknowns by 50%. I'm like, all right, this ain't bad. This is pretty sweet. Okay, so now let's think about what we want to do now. How can I start eliminating other variables? Well, let's think about this. this equation right here, I don't want to get rid of ID. So I want ID to remain. So I'm trying to always like either use I1 or I2. I'm trying to substitute into I1 and I2 and leave ID. So let's take a look at what might happen if I substituted this in its current form, let's see, into one of these two. This equation has I2 and ID. This one has I1 and I2, and I recognize it's like, check this out. What if I substituted I1 into here? I would then have this equation in terms of I2 and ID, and I would have this equation in terms of I2 and ID, and I could get rid of a variable I1. So let's watch it. So here I go. So I'm going to go ahead and I'm going to take this right here and I'm going to substitute it into this dude right there. So here it comes. It's going to come over there and do that. So here I go. I'm going to give myself a little bit more room because now it's starting to expand in terms of the numbers and variables I have. So I'm going to say 3 is equal to, and I'm going to put 100 multiplied by I1. So I'm going to have this expression right there, I2 plus ID, and then plus 50 times I2. All right, well, let's rearrange that. So I'm going to have 3 is equal to, let's multiply 100 through, so 100 times I2 plus 100 ID plus 50 I2. All right, well, let's reduce that. So I've got 100 I2 and 50 I2, so I can actually get down to 3 is equal to 150 I2 plus 100 ID. Now, look at this. This is pretty amazing because now I'm down to 2 equations and 2 unknowns. So I have an equation right here, which is in terms of I2 and ID, and I have an equation right here, which is in terms of I2 and ID. And it's like, oh, this is so awesome. So now what I need to do is I need to somehow plug these into each other and get rid of I2. So now when I look at this, which one would be easier to rearrange? This one right here appears to be easier because I have I2 on the left-hand side, and I just need to divide 50 through on the right, and it would isolate it. So let's do that really quick. Let's rearrange this. I'm going to divide both sides of the equation by 50. So I'm going to say I2 is equal to 100 ID plus 0.7 over 50. And now I'm going to say I2 is equal to 100 over 50 ID is equal to 2 ID. And then I'm going to have 0.7 over 50. And I'm just going to leave that right there. I'm just going to leave it in the fractional form. I did that because it is time to do the final substitution, which is this dude is going into that dude. And now what I'm going to do is luckily I've come down to this point right here where I can actually write this out a little bit longer. So I'm going to kind of draw a little line right there. And here I go. Here we go. All right. So I'm going to have 3 is equal to 150 multiplied by I2. And so I'm going to have 2 multiplied by ID plus 0.7 over 50, we'll just leave it as is, plus 100 times ID. Okay, now we're getting there. Now let's multiply 150 through this one, and we'll get 3 is equal to, and I'm going to have 150 times 2, so I got 300 ID plus, now I left it in this form because it's kind of neat, 150 times 0.7 over 50. So it's basically 150 divided by 50 is 3. 3 times 0.7 is 2.1. And then that's the multiply through there. And then we have 100 ID. We can combine these terms here. So I have 300 ID and I have 100 ID. So now I'm down to 3 is equal to 400 times ID plus 2.1, and holy cow, I'm getting close. So now let's subtract 2.1 from both sides. So now I'm left with 0.9 is equal to 400 ID. And finally, I can divide both sides by 400, so I get ID is equal to 0.9 over 400, and that is equal to then, bring out old buddy here. Went to sleep, it's taking so long, but that's all right. Okay, bop, bop, bop. All right, here we go. 0.9 divided by 400, boom. 225, 0.00225. That's equal to 2.25 milliamps. Okay, so that is 2.25 milliamps, and boom, I have my first unknown. So that was awesome. The first unknown takes the longest, okay? Let's be honest about this. It takes the longest, and I ended up getting it. So now the question becomes, how do I kind of unfold all this? Well, it turns out it goes really, really quick. So let's see if I can do this all on the same piece of paper. So I know that ID is 2.25 milliamps, okay? I'm gonna come back up here, and I'm gonna do a little scratch paper here. If ID is 2.25 milliamps and it goes through V3, I know that V3 is equal to 2.25 milliamps multiplied by 100. And I can immediately calculate V3. So I just take that and go times 100. Boom, I got myself 0.225 volts. I now have solved for my second variable. Holy buckets, check this out. If I know that V3 is 0.225 and this voltage is 0.7, I have KVL around this loop and I can find V2. So look at V2 right here. Well, V2 is equal to V3, which I just solved, 0.225 plus 0.7. I can say V2 is equal to, add 0.7 to that, oh boy, oh baby, 925 volts. I just have solved for my next one. Oh, so now I'm sitting here going, this ain't too bad. I was only looking for ID and V1, V2, and V3. So I've got ID, I've got V2, and I've got V3. How do I find V1? Well, oh, look at this one. Look at this one. I've already written KVL around this loop. 3 is equal to V1 plus V2, which is 0.925. Look at this. I just basically subtract 0.925 from 3, and I got it. So basically, I'm going to do this. I'm going to say make that negative, add it to 3, and I get this is equal to 2.075, and I think I have it. And boom, I did it. I have just solved this. Now take a look at this. This was involved, I would say. I mean, we're like 25 minutes into this, but I mean, that's electrical engineering, right? I mean, this circuit had 6 unknowns, okay? 6 variables that you had to solve for, and you had a nonlinear device in here. So the first thing you had to do with the nonlinear device was figure out, is it on or is it off? And so you had to go through an exercise where you had to figure out what the minimum voltage was for the power supply. And we figured out that in order for this to be on, this power supply had to be at least 2.1 volts. Then we said, well, if we're given that it's 3, it is above that. And so that means it's on. So then that allowed us to put in the constant voltage drop model for the diode when it is on, meaning that we replace it with a 0.7 volt DC power supply. And 0.7 is the forward voltage spec of the diode. From there, we were back to our original resistor and voltage source circuits that we could then write equations using Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law to describe the circuit. And then it was just a whole pile of algebra that we did, and we succeeded. All right, nice work. That was it. And that is all. See ya.